We're back. All right. That. Here we are. So really, the watchwords are insoluble water. This is where we get more about shape. What makes them the absence of oxygen, the presence of mostly carbon and hydrogen and carbon-to-carbon bonds. Those are the definition of non-polar covalent. You might remember when you have a lot of hydrogen bonds, SH, OH, pH, and NH. Not pH like in pH that we were talking about earlier, but phosphorus and hydrogen, sulfur and hydrogen, nitrogen and hydrogen, oxygen and hydrogen. Those are the ones that are capable of forming those polar covalent bonds like water. So when you have carbon to hydrogens, okay, and you'll find this when we start talking about things called saturated fats. It means they've got the maximum number of hydrogens they can have. All of those non-polar covalent bonds are sharing the electrons equally. And because of that, they are just incompatible with something polar like water. So we call them triglycerides, as you will see shortly. And then we move on from there. Triglycerides, you get fats when they're solid at room temperature, oils when they're liquid, are in this category of lipids. This is sort of we start with this one. We basically form the other ones, mostly from this, until we get down to things like cholesterol byproducts, and when we get down into something called, as you'll see that the terminology they have is something that makes prostaglandins. You'll see that very shortly. And we deal with that in different chapters as well. We're called eicosanoids. So what you're going to see here is we have something called linear hydrocarbons, and that accounts for the shape and our ability. And so I was talking about before we had that mini break was density, how closely packed. So you have linear hydrocarbons and you have glycerol. When we're talking about carbons, we have 3-carbon sugar, which makes this sort of an unusual sugar, everybody, is what's called a sugar alcohol. So you have, when you have a 3-carbon, it has hydrogens, you don't have to know the chemical structures. All around it like this, you'll notice it has abundance of protruding OHs. The more OHs you have, the more likely it's an alcohol. And so but it still has that C3H6O3 carbohydrate, so we call these sugar alcohols. Sugar alcohols are pretty interesting. Our bodies use alcohol very similar to the way we use sugar. Indeed, alcohol itself is ethanol that we have like in alcoholic beverages actually is metabolized first and then carbohydrates. So they're very, very similar in their degree of energy production. So we call that a sugar alcohol. The name for it is glycerol, as you can see by the screen. So here's the glycerol molecule, a sugar alcohol, and you'll see it, and they have it drawn out with what are called linear hydrocarbons. And again, dehydration synthesis, energy storage, which is what fats use in our bodies, insulation and protection. All of those are absolutely correct. Your heart has fat around it, your kidneys have fat around it, your spinal cord has fat around it. So that's protecting and insulating is really what it is. Not so much energy storage there, but energy storage in other areas for fats. And so this is an example. We call these a long chain fatty acid. Linear, so you have to go, this is 3-dimensionally linear. Even though they draw this sort of in a zigzag, it's still overall, if you would get those Tinker toy models and put them together, effectively it would be linear, certainly for the purposes of how it is sort of more or less to describe it as packed. Okay, and I'll show it how we do it schematically, or we sort of do a representation of it. And you can see it's all carbons in this case. They all have single bonds and they have the maximum number of hydrogens. That's what we call a saturated long chain fatty acid. So it's somewhere, long chain means 8 to 20 carbons in that particular chain. And at the end of it, they have this. They have all of that. And at the end of it, they have something called C double bond OH. That's a carboxyl is the name of it. CARBOXYL group. And that is another name for an organic acid. And depending on what it's hooked up to, it doesn't have to be a whole long carbon. It can be hooked up to anything. And some organic acids are strong and some organic acids are weak. That's not a big deal. Okay? That's what you're dealing with. So basically what's happened here, when we hook up, it doesn't matter whether it's the H from here or the H from here. What an organic acid has is that C double bond OH. The C and the two O's together are fairly happy together. They don't mind losing the H. Again, depending on what they're attached to, they might lose it very, very rapidly. So they're willing to give off that proton and be C double bond O with a minus charge fairly easily. That's what makes them an acid. We donate the proton. So what they have is they're able to donate from that OH group and pick up the H, for argument's sake. Again, it doesn't matter, they're basically equal, from that sugar alcohol. That linkage has a fancy name in organic chemistry. When you mix an alcohol, which is the glycerol, and an acid, they link up to form something called an ester. That's chemistry, but the way we represent that is called IED. I beg your pardon, IDE. So when you see triglyceride, it means there's 3 fatty acids, all linked as esters to glycerol. Tri, there's 3 of them, glycer and I, tells you what it is. That's how you would identify them. This is our main storage unit, and you can see by the design, it's very uniform. The chains don't have to be the same. Indeed, the chains can be different, but all of those have the same number of hydrogens that surround them, maximum. So that's a saturated, those are 3 saturated fatty acids. So if you draw them schematically, they look like this, or they look like this, or they look like this. And that's the analogy with the books and records in the box. You can pack them in. If we had all tables of just tabletops and they didn't have legs, we could get a whole bunch of them stacked together. They'd be very dense, very heavy, solid, room temperature. But if they all had legs on them, it would be tough to get more than a couple of those together. It'd be really awkward. Or a whole bunch of chairs. They're not terribly uniform. Maybe you could stack a couple. That would be the opposite. That would be an oil. So what you're going to see very shortly is every so often, in our systems, it happens with some degree of frequency, we have what's called a site of unsaturation. What that means, looks like this, and one of these has a kink. That's because rather than being single bonds, there's a double bond. Go back to the Tinker toys, those 2 little springs. The idea why it's linear can form because it can go around 360 degrees. It means you put a spring, double bond in there, it loses that freedom. And effectively, if you want to think of it biologically from a structural standpoint, it develops its irregularity. The more you have of those, the harder they are to pack. So when you have 1 or more, 1 is called a monounsaturated fat or lipid. And then you get anything more than 1 we call polysaturated. Actually, if you want to think from a nutritional, and I don't want to be a nutritional, I'm not really qualified. If you wonder, in school, Dr. Robbins, Dr. Short, I'm trying to think of who's teaching, Dr. Maurer, who you might have down the road. All of us probably could handle teaching nutrition. in order to get certification in nursing and probably in health sciences, in order to have a valid nutrition course, it has to be taught by a registered nutritionist. Okay. That's something we didn't used to have here before, but now we just the rules keep changing. I mean, I understand a lot of the stuff that we have to do here is because of certification. Because if we're not certified, then you get a degree from an uncertified program. It's no bueno. Not good. So we all, and so I certainly don't know that much about it. We all, because I can flatter myself as knowing how being a self-taught cook. Leaving the kitchen very sloppy. So voila, it looks like this. And here's I was having trouble playing this. I don't know if it plays here. It's very short. We do quite a few of these. There's nothing special about this one. Let's see if it plays.
Butter, lard, margarine, and celery are composed of lipids called fats. To make a fat molecule, 3 fatty acids bind to a molecule of glycerol. For this reason, fat molecules are technically called triglycerides. Fat molecules do not mix with water because they have 3 long hydrocarbon tails. Cells use fats for energy storage because the tails hold more potential energy than other biological molecules.
That's a very short one. That's why I like to use these PowerPoints, the animations, when we get to them are brilliant. So that's a saturated, what you were seeing in there, maximum number of hydrogens, maximum amount of energy. They're packed solid with energy. You get much more energy per unit with a fat than you do a sugar. The bad news is what happens when we start chopping up fats, we end up with waste products that can be particularly problematic. When we chop saturated fats, not as many. When we chop up unsaturated fats, particularly poly with many unsaturated fats, we release a lot of what are called free radicals. Free radicals are unpaired electrons. They are the basis of modern cancer theory, modern deterioration, aging theory. We have mechanisms in store to combat those. We generate a fair amount of them, and the idea is to limit. That's why we have, unfortunately, bad habit or exposed to chemicals. All of those, alcohol, smoking, chemicals, particularly potentially illegal chemicals, or chemicals that are made by who knows what. I mean, all of those have the capacity to do a fairly large amount of harm. So I bring that to you to understand kind of what it's all about. The other thing that happens with those kinds of, you'll see that what we do with them is we do bad things to them to make them into saturated fats. In general, from a nutritional standpoint, what I was starting on before, if you had a diet that was strictly monounsaturated fats, you'd be doing very well. I mean, the classic ones that are used a lot today, extra virgin olive oil, or olive oil in general, as long as it's not really something that's been altered, and avocado oil are both very, very useful. Avocado is more expensive. We happen to use that at home. It has a higher smoke point for certain dishes. We use the extra virgin olive oil, which has a lower smoke point. It all depends on what you're cooking, because of the flavor with the extra virgin olive oil. But the reality is if you go to southern Italy or Sicily, that's all they use is olive oil. That's the only fat they use. As you go farther northern, there's more cows. And therefore now you're starting to get a little more butter, and eventually you get more and more butter. And as you get to northern Italy, Piemonte and things, they use more lard because the pig in Italy, the pig is king. Just to give you an idea. So a lot of it is cultural. It's like that. Those things. So what we do, as you'll see when we talk about saturated fats, one of the big problems with polyunsaturated fats, not just the fact that when you chop them up, you make free radicals. When you chop them up, they tend they have like 2 carbon molecules. They slam into each other, and they create even nastier molecules called trans fatty acids. And they do a really serious number in the interior of your blood vessels and promote deteriorations, particularly in people getting to middle age and beyond. So there's a whole lot of reasons beyond it, and they're hidden. because fatty acids are stable, particularly saturated fatty acids, but they're expensive. Avocado oil, if you go out to the store and price avocado oil and extra virgin olive oil, it ain't cheap. So what do they use? They get inexpensive oils like vegetable oil, corn oil, canola oil, which you go to Aldi's and see how inexpensive that is. And basically what they do to make them shelf stable and utilized in cooking and foods, they blow hydrogen into them. So they hydrogenate polyunsaturated and various degrees of unsaturated oils to make them solid. It's short Crisco, whatever you want to call it. So it's shelf stable. I mean, you buy Crisco in bars, you don't have to refrigerate that. As long as they're sealed inside there and the bugs can't get at them, they're fine till next year. When you're gonna make that chocolate chip cookie recipe or whatever recipe you're gonna use, that's the way it works. I'm not telling tales out of school. And in colleges because you have dorm rooms, you don't have a lot of refrigerator. You buy crackers, you buy cookies, you buy all that stuff, and as long as it's sealed, it's fresh. I don't know about you, but I buy cookies in the dorm. Once they open them, they're not hanging around. Like those Oreos aren't even making it home in the car when you get them. Just say it, the mid ones. So all of that type of thing. So that's the whole idea. Animal fats, butter, lard, all of those things. They're all solids at room temperature. So they're just showing you the differences between there's no double bonds. Unsaturated, we have trans fatty acids. Okay, modified unsaturated fatty oils that resemble the structure of fatty acids, considered unhealthy. Okay, it's all the assembly. So, I mean, to compensate for, like I said, we bought salmon at Sam's Club. I don't know if I mentioned that. That's rich with omega-3s. I'm trying to compensate for all those muffins. They're just nothing more than sugar. Plus carbs. And so you use that. And that's why, as time has gone on, we've become much more aware of foods like that. And so the difference between omega-6s and omega-3s, understanding that is really important for a lot of it. Depending on where you're going career-wise or just family-wise or individual-wise, it's helpful to know all this. It's a lot different than the old when we were kids type of thing. Nobody knew any of this stuff. What was on sale at the supermarket, and you went from there. Okay, and here's the difference. That's the site of unsaturation. Typically, even just one of those can make something potentially into an oil. You will see that in our cells, typically the way, if you look at our typical triglyceride in our cells, it's not quite like that. It's still considered a fat because typically the structure looks like this. We have two long chain fatty acids that are saturated, and we have one that has one side of unsaturation. Because we have two that are saturated, effectively this still packs pretty decently, using the packing analogy. Okay? That's what it looks like in our cells. You see, I'm drawing it that way for a reason. And this is the reason. The important part to understand are phospholipids. What we basically do, we may use these as they are, but what we do biologically more than anything else is we substitute enzymatically, which means the body has a chemical way of doing this. They take away one of the fatty acids and insert what's called a phosphate group, PO4 with a negative sign. These are negatively charged. And because negatively charged makes it inherently, because it's charged, water soluble. These are still long lipid tails. They're fat soluble. They are incompatible. They don't like each other. It's the Steelers and the Ravens lining up. There's going to be a fight. The referees are doing everything to separate them. You don't have to worry about referees here. They separate themselves. And what happens, we see biologically, this is what occurs. We call the phosphate head rotates up in this direction to get as far away from those lipid tails as it possibly can. So we have a water-soluble polar head and lipid tails that are water insoluble. Voila, what do we have? A phospholipid. That's critical. They're the foundation of all living membranes. You're going to see how they assort themselves when we put them together. Again, you have a bunch of lipids, even like that. They don't bond together. It's just that they're either water, in this case, they're fat compatible. They just naturally come together. The gravy from the turkey, put it in the fridge, comes to the top. Just let it sit. Take it out, even if it's not in the fridge, it'll come to the top. Put it in the fridge. Because it's an animal product, it'll probably solidify with temperature. So that's really important to understand. So we see this construct here. And notice, so we having lab after this? Oh, lucky God. That's a day and a half. 3 hours a meeting, 3 hours a day. There's an ibuprofen with your name on it someplace. But you had all the stuff about connective tissue. Right? In the membrane, it's composed of these phospholipids. Most of them have some kind of nitrogenous structure on them because other things can attach to them. Sometimes it's a little short change of those monosaccharides. Those give it an identity that we're going to look at when we get to cell membranes. That's why maybe you have A positive blood and you're compatible with my A positive, or you have her O positive, which is not compatible, or her B negative, is a B positive. All because of short chain carbohydrates. You did connective tissues. So you had a fibroblast here, and you had a fibroblast over here. What makes them connective tissues, they're connected by fibers. Fibers have to have something to connect to. All those collagens, it's not like they're, oh, I see a nice looking fibroblast here, I'll latch onto it. No. Sticking out of its membrane is going to have something that this can attach to. Furthermore, those phospholipids can have other things that go onto it, and it can develop in the bloodstream kinds of fats that can cause a lot of damage. And they form something because they form proteins, and the protein structure forms a base term called a mycel, and it surrounds fatty components so they can travel through the bloodstream. And they combine something that you'll learn about when you get to cardiovascular, and probably more so in nursing and health science, called various densities of lipoproteins. VLDL for very low, LDL for low, HDL for high. Not going to do the unit now, but when people get to like my age, and certainly starting about age 40, you start worrying about whether you're at risk for a heart attack or a stroke. So what they do is they take your blood and they see what kind of lipoproteins you have. If you're very active, you have a lot of HDL, heavy lipoproteins. They're really high density lipoproteins. That's a sign of exercise and activity. If you're just sitting here eating a bag of chips after a bag of chips and candy like that, you have a lot of very, very low ones. You're in trouble. And we can relate, there's a ratio that was created at the University of Massachusetts back in 1980, it's used all the time, as a predictor on whether you're at greater risk or lesser risk for having a cardiovascular heart attack. So all that's part of it as well. There's so much that goes on. Oh my God. Hold on one second. They just shot at the University of Utah about noon. I don't know whether it was Utah time or not. A guy who's kind of a conservative speaker for youth, shot and killed. father of 2 young kids. That's the text my wife gave to me. Named Charlie Kirk. Bad when violence and politics meet. Very, very bad. As far as I'm going to go with it, it's just terrible. Here's what happens. All we have to do is put those phospholipids in water without all the stuff that connects to them, and they do this. They form the very, very famous phospholipid bilayer. What that is, okay, is phosphate heads that are nonpolar. They naturally move away, and we call them hydrophilic because they like water. They want to move as far away from fats as possible. So inevitably, the fats are hydrophobic. They hate water. They move together. And so they kind of go, heads are away and tails are like this. And again, to draw it in my poor artwork schematically, what a membrane is the fatty portion here. So whether it's a cell membrane, whether it's a membrane of mitochondria, a nuclear membrane, a lysosomal membrane, it doesn't matter. Whether it's an organelle's membrane or a cell membrane, it's a membrane. The boundary are the fats. And again, they're not tethered together by bonds. That's why proteins can stick in them. That's how we're going to start to develop when we get to the cell, what's called the fluid mosaic model. The polar area, water compatible, because outside the cell is a water-based environment, and inside the cell is a water-based environment. So even though it's relatively compared to the girth of what you think is a boundary, it's tiny. It's almost like you had a water volume here that wouldn't collapse, water here and water here, and you had like a piece of saran wrap separated. Amazingly enough. I mean, that gives you somewhat of the scale of what sometimes it could be like. But it's strong enough to keep them separated, and the beauty of not being tethered together, it can open and close. How's that? It can open and it can close. As we continue to move on, that's the phospholipid bilayer. More of that when we get to the cell. It's really important to understand. Steroids. People, oh, I hear steroids, oh, bodybuilding steroids, anabolic steroids. Yeah, there's a lot of the stuff is bad. All of us make anabolic steroids. Women to a lesser extent, and you'll learn in your adrenal glands. It's the only source of testosterone in women. It plays an important role in 2 things. Scientifically, it plays an important role in making sure there's adequate red blood cells, and it plays an important role in sex drive. Okay? They become obviously more prominent after puberty and beyond. In male, we make testosterone both in the testes and in the adrenal gland, this aspect of the adrenal glands as well. Estrogen, progesterone, testosterone. We hear about cortisol. A lot of people know about cortisone. Have you ever had to take a dose back because you had poison ivy or a bad rash, or know somebody who did? That's made from something called cortisol that we make in our adrenal glands as well. We make a ton of products that are vitally important that are made from fats. And the fat that they are made from is cholesterol. Hence, we give them the name steroids because they're made from the thing called sterol. All animals have cholesterol in their membranes. That cholesterol molecule stabilizes the membrane so they can open and close and yet still remain intact. It's not like they open and all of a sudden they dissolve. This plays a vital role in the understanding of membranes that are there, as well as making all these other things. So you can find it in almost any animal products there. It's a framework for making vitamin D. And without vitamin D, we don't get enough calcium, and calcium covers a whole lot of things. Bile salts, the only way you can digest fats is with fats, because you have to use fats to separate fats into their components, just the way it works. And the stability and the fluidity, the ability of a membrane to open and close, to change shape, is so vital, as you will see as we go on. It's cholesterol. So This whole, oh, cholesterol's bad. Certain diets that produce a lot of bad fats are sometimes erroneously called, it's not about cholesterol, it's more about carbohydrates. Years ago, they said, oh, we're going to take a whole line of baking products that had too much cholesterol in them. So we're going to stop having those there. They were called snack rolls. They were all made out of sugar. They were much worse when they evaluated people who made that their cookie of choice or their baked good of choice. They were made out of sugar. Oh, but they're cholesterol free. Everybody went cholesterol free. You need that stuff. We make a lot of it, but we still have to ingest some of it. That's there. This is what cholesterol looks like. These four rings is the backbone. If we basically, in a membrane, we use the whole molecule. We lop off some of these side chains, and when we look at the chemistry of what estrogen and progesterone and testosterone look like, they're almost identical. A few little chemical substitution, they have these four ring nucleus. Every time you see a ring without, on a point like that doesn't have a name, it's carbon. So this cholesterol, as I offhand, has 27 carbons. I think the rings together have, I don't know, 21 or 22 carbons, something like that. But cholesterol is everywhere. I can't stress enough. These four interlocking hydrocarbon rings, that's really the critical piece that we make all those important chemicals from, that we call steroids. This is the idea of something being essential. Okay. Fatty acids. These make something that's interesting. They're called prostaglandins. You look at them in the immune system in AP2. They're interesting because they have a couple of sites of unsaturation. And because of that, we can actually make this long chain fatty acid change shape and almost, for lack of a better way to describe it, turn from linear into almost like a form of bond here, like almost like a hairpin. So they're really long with a couple of sites of unsaturation and an acid at the end, like one of these would have a C double bond OH at the end. You don't have to know the chemistry. And they're called prostaglandins because they were isolated from the prostate. They are in a pivotal role in all of these things. Blood clotting, blood pressure, inflammation, labor. They're so important. So back to that, from the headache I'm giving you, and hopefully Dr. Robbins will amplify, you take that ibuprofen or an aspirin or a Aleve, they are called non-steroidal anti-inflammatory drugs, or NSAIDs. They inhibit prostaglandin synthesis. That's why they're anti-inflammatory. They stop this process from going on. So these eicosanoids are derived from something called arachidonic acid. There's others. It's essential. We can't make it. We have to acquire it through diet. So it's an essential fatty acid. Good news. See, there's a lot of good things in life. You know where you find arachidonic acid? One of the sources, the one I use the most, is peanut butter. I'm a peanut butter avid. Peanut Butter Anonymous. I've gone there. Hi, I'm Lou. I've been sober for 0 days. Hi, Lou. Just saying. Don't like peanut butter? Oh, what are you doing? I mean, enough of that. Enough of that tomfoolery. That's AP2 stuff. We'll save it. Let's introduce proteins. Get this finished now in a half an hour and then send you on your merry way. Maybe less. Proteins are big. Cells, 20 to 30% of our mass. Bodies, most of the proteins in our body, most of our weight comes from muscle. Pretty much all protein. Skeletal muscle is almost all protein. Okay. Nice little flexible tubes of protein. They are vary in function, structural, chemical, movable. That's what we spend an inordinately long amount of time in the second half of this course talking about things that can change shape and conduct impulses. That's when we talk about muscle and nerves. That's really the heart to me. Bones, muscles, and nerves, the heart of AP1. I love bones because I know the most about that. Okay, so as you'll see, unlike we don't see that calcium and phosphorus, you see a little bit more sulfur, but it's not a big deal for me. CHON with sulfur and phosphorus. That's one of the ways we track proteins. We can tag sulfur with a radioactive agent. So when we're trying to look to see if it's something is due to a protein or something is due to, and we radioactively tag phosphate to see if it has to do with DNA or RNA. That's an aside. So there are and this is monomers, polymers, except it has, unlike glucose being identical, these are something called amino acids. An amino acid is a very interesting molecule. Okay, because they're not identical by definition. There are 20 of them that we use, and depending on the author you read, 8 or 9 of them are essential. What essential means, we have to acquire them through diet. So if you're eating an animal product, you're getting all your essential amino acids. You have, whether it's a glass of milk, whether it's cheese, you're getting it. Whether you're eating a burger, not like one of those vegan style burgers. So complete protein indicates it has all of those. The problem with you make a complete protein, this is where people who are vegetarians can have dairy. Not a problem. Frequently they'll eat eggs and dairy. Those are all complete proteins. Vegans don't eat any animal products. And the problem is they have to have different combinations. Even though we didn't know it at the time, people found out that beans and rice made a complete protein. Beans are in a category called legumes, and rice effectively is a seed. So you had to have a legume and something in the nut or seed category. If you like hummus, chickpeas, legume, and you use sesame seed paste, tahini, and put those together, and however you flavor it, and you have hummus. And people, I love the stuff. You'll love this. I mentioned it already. There is one legume that's a complete protein. Tofu. So tofu is unique, and not unique is maybe the wrong term. It's one of the most commonly utilized soybeans, which is what it is. It's basically soybean curd. If you didn't know how they make it, they take raw soybeans, they take very, very pure water, and basically they buzz them around, let them soak in the water, buzz them like in a blender or a Vitamix, and you add a chemical to them, and it causes them to separate. And you'll form the curd will come from that, and basically the curd's filled with water, and as long as you just keep squeezing it, and you get tofu. So that's the difference between firm and extra firm, silken, and all that stuff. Good stuff. That's a complete protein. So that's sort of the back structure with this. But what's unique about them is they're all made of amino acids. You can have ones that are structural. You're going to see structural ones are formed differently, and typically structural ones, this is collagen, okay, are insoluble. Found in connective tissue. It's the most abundant protein in our body, responsible for bones, tendons, ligaments. You probably got all that when you were doing that section on connective tissue, right? Probably got a lot of that stuff over with Dr. Robbins, waving to over in lab. If you notice the way that they're put together, it's like this. You're going to see they're braided or intertwined. It's because it gives them strength. Typically, they are insoluble. Interestingly, they don't change dramatically unless they're being heated for long periods of time. We'll get to that. Enzymes, it's about shape. Transport, hemoglobin, it's about shape. It's all about the shape that's there. These are different. You're going to learn they're called globular proteins. Contractile proteins, it's about shape. This is how muscles work. This is actin, and this is myosin. Chemical messenger proteins, we'll get involved in those. All these, we look at the cell. Antibodies, proteins that look like a letter Y. they're surrounding a virus. This would be like a common cold virus. Okay. They latch onto it, and by blocking it here, it doesn't allow it to attach to other things. If it can't attach, it can't hurt you. Moreover, when they block it with all those things, it makes it easily sort of tags it and identifies so white blood cells can come along and gobble it up. There's a myriad of things that proteins do. And we'll get into all of them. They're all made of amino acids, and they have a very special bond called the peptide bond. You'll see it in a second. What makes them unique is their structure. They all have a central carbon, and on one side you're going to see they have that C double bond OH. That's the acid. And the amine, you'll see shortly, the nitrogen, two hydrogens called an NH2. That's an amine. So amino acids, one side is acidic, the acid, and the amine, or not, the NH2, is basic. So they neutralize one another. But what makes them even more different still, that they all have that structure. That's what I mean when you talk about monomers and polymers. As long as the base structure is, if not the same, like with glucose, but similar, like amino acids, they differ by what's called the R group. And the R group could be as simple as just a hydrogen or a very, very large, complicated molecule, none of which you'll have to know the names of. That's biochemistry for us. Students who are in this very room at 11 o'clock, Monday, Wednesdays, and Fridays, are all being tortured by my colleague, Dr. Hillwig, and they have to learn the names of all 20 amino acids. Voila. Said structure. Essential carbon, double bond OH, the acid, NH2, the amino group, another hydrogen here, all different, and the R group. And again, the R group can be one of 20 different things, 8 of which most authors agree, 9, I think, from this author, that we have to acquire through diet. So all are made up from 20 of those. They're joined together by a particularly strong, a lot of energy in proteins, peptide bond. It's a joining of the amine from one and the acid from another. They can either act as acid or base depending on what the R group is. And I'll show you what the bond looks like. Here it is. Once again, here's R. Let's assume they're the same for argument's sake, that they have the same R group. It doesn't matter. This is here. The OH, in this case, they're taking the OH from the C double bond OH, the carboxyl group, one of the hydrogens, and they form this bond where you have C double bond O, and you don't have to write it or you don't have to know it, just know the name, and you bond it to the end with an H. It's called a peptide bond. This is confusing. When you have two amino acids, and you bond them together, they call it a dipeptide. Theoretically, that would mean they're two peptide bonds. This is another one of those just because. Dipeptide is the number of amino acids. Tripeptide, there'd be 2 peptide bonds, 3 amino acids. I'm sorry, I didn't make this up. I could send a certified letter to the chemistry people, they would throw it away. This confuses students. We're not changing it. An old saying about City Hall and fighting it. So that's really the issue. All those bonds, it's extraordinarily strong. It's a fancy name. It's called remember when I wrote the name ester, because you don't have to know this is called an amide, A-M-I-D-E, you don't have to know. If you're a chem major, you have to know it. And really everything is based on the sequence of amino acids. There's 20. You have an infinite number of these. The difference between a polypeptide, which is, let's say, more than 4 of those amino acids, okay, and a protein is numbers. You have 100 or more amino acids linked together with peptide bonds. We call it a protein. If you have 99 down to like 4, it's a polypeptide. So they're not different. Proteins are bigger and stronger. No, they're longer. Are they stronger or no? So don't get confused by that. It's just names. In this case, that's just a size differential or a length differential. Hemoglobin is a protein. It's made up of 4 polypeptide chains together. They make a protein we call hemoglobin. Insulin is a protein. It has 2 polypeptide chains together. They're big enough to qualify as a protein. So it's a little silly. What's the interesting thing is they can form. They have what's called a primary structure. It's a battery. What's that? It's like a baseball batting order, 1 through 9. Look for 9 of these amino acids. That's going to determine what it's going to be. We call that the primary structure. So they're talking here primary, the linear sequence or order. What happens, it'll do one of 2 things. It will either fanfold, and this is part of the thing that creates a really significant feature in anatomy. How does our brain fit so well in the skull? When it's much, much bigger, it fanfolds on itself. How does that 20 feet of your digestive tract and how does your stomach, small intestine, large intestine, basically 2 that's about 1.5 inches and or maybe a little bit more in diameter, have the surface area of a tennis court? So it fan folds. We call that a pleated sheet. Or it doesn't have to do that. It can basically, I'll go to great expense. Twist. They form a spiral. Alpha and beta are just directional terms. So they're called alpha. Alpha means a right-handed spiral. Turn to the right. And beta is sort of a left-handed pleat, which I probably can't do. So accordion, very good. And that's what we do. We see a lot of that. You'll see so many of this. I will make an effort to point it out wherever I can. That is the secondary. So how they interact with each other, that is determined by, you're going to love this. Remember what I said before. Hydrogen bonds, OH, 10H, SH, pH. You have an abundance of these in amino acids. So you have an abundance of hydrogen bonding that occurs. The determination of whether it's going to be an alpha helix or a beta or a beta helix sheets. British friends call them beta sheets. I had a biochemistry professor who was British. Vitamins were vitamins. Schedules were schedules. I didn't like him anymore. Used to call him King Vitamin. Cereal. If it's not Fruit Loops, why have it? Okay. Tertiary involves other interactions. Tertiary has to do with the R groups. And the R groups fall into 6 different categories. The R groups, depending, I'm not going to ask about the chemical structure, can be either acidic, basic, positively charged, negatively charged, water soluble, fat soluble. There's an old saying, about how they kind of come together. Okay. Acids and bases combine to neutralize each other. Positive and negative subtract. They combine to neutralize. Water-soluble things go with water-soluble things. Fat-soluble things go with fat-soluble. We used to say likes, like. Like things like to go together with like things. That's basically the way it works, sort of in a chemical basis like that. So the tertiary structures have a lot to do with about their shapes. So if you have tertiary structures like this, You might have a mixture of pleated sheets, and spirals. Based on those interactions. Those are not so. Secondary structure, hydrogen bonds, tertiary structure, those different factors, different things that involve the R groups. Quaternary, all that means is that you have different ones, and you saw it before. Here's hemoglobin. That's a quaternary structure. This is a polypeptide chain, not the reddish color, but in the brown, those are called alphas. These are called betas. So there are two pairs, two sets of identical, two alphas, two betas, that come together, and each has a heme unit to carry oxygen in the middle of it. So those are four polypeptide chains. They come together to make a protein. That's a quaternary structure. Fancy name that you don't have to know. When they involve metal, like hemoglobin, iron, is called a metalloprotein. Conjugated. Doesn't really matter. So here you go. Here's the primary structure, the batting order. Here you can have either pleated sheets, and notice the little dots, hydrogen bonds. Hydrogen bonds. Easy to form, easy to break. So you can have an alpha helix, hydrogen bonds, zigzags, hydrogen bonds. This is the classic. The vast majority of our proteins form this sort of globule. They mix up, all of these kind of mix up together. So you have some areas where you'll have these little ribbon-like structures. Some will be more pleated structures. And so the tertiary structure is something called transthritin that transports the thyroid hormone, thyroxine, blood and cerebrospinal fluid. So superimposed secondary structures of alphas and betas to form a compact molecule. And so a lot of them, enzymes and things like that, are in that category. Quaternary makes that two or more chains they're each with their own tertiary structure combined. And so here they're getting a better look at this one that can transport thyroid hormone. Is fat soluble, not water soluble, interestingly enough. And so you can see some of those things. I don't know if this is very useful.
Most proteins are folded into a complex globular shape. Each protein molecule consists of one or more chains of amino acid monomers. The amino acids are linked by peptide bonds, so a protein polymer is often called a polypeptide. Because they are so complicated, proteins are usually described in terms of 4 levels of structure.
That's primary, secondary, and quaternary. So normally what happens when we talked about earlier, heat, pH, and you can see all that they are. Tertiary, quaternary structures, 3-dimensional. They have sites we call active sites. That's where reactions occur, and we'll get to that. Antibodies, hormones, molecular chaperones. That's molecules that are proteins that escort other things, like I'm trying to get the best way to describe it. They'll help to transport RNA to certain areas or transport proteins to certain areas. When you talk about a chaperone, it's just a score like you have a chaperone appearance for kids at the prom from high school. And enzymes that you can use over and over again. They have definite shapes, and I'll get into drawing that. And so whether it's the multiple polypeptides, quaternary, whether they're globular proteins like that, when you have extremes of heat up or down, pH up or down, what happens with all of those is they begin to separate. They go back to they lose their tertiary structure. They lose, without being too bold about it, their secondary structure. What's left, heat, changes in temperature or pH. All that's left is the primary structure. Call that process dehydration. They lose their nature, they lose their shape. The one that's a little bit different, what they're talking about there, these are the globulars. Denaturing, unfolds, and lose their functional 3-dimensional shape. Fibers are more stable, okay? When you denature, the active sites disappear, whether it's acidity, whether it's usually it's increased acidity or increased temperature, and usually reversible if you get to it in time. Irreversible, uncooking an egg, etc., etc. Fibers, proteins, why they're more stable, okay, they're structurally collagen, elastic. So basically, they're made of helices that break. So if I take this, and I do this, it will work. I can get that too. But if I take this and braid all those together, guess what? We would do this in surgery. We take monofilament steel and we twist it and twist it. We fold it in half, and my assistant would be on one side, I'd be on the other side, and we twist it and braid it much stronger. That's everybody, that's what a fibrous protein is. Braiding. So even though you heat it or you alter the pH, it stays. If anything, it gets tougher. It's kind of good news and bad news when you cook something like that. Fibrous proteins get to the point where they're absolutely inedible. So it's kind of that structural stuff. It's when you have like meat or something, you talk about gristle. Okay, it's like not edible. So enzymes, globular proteins act as catalysts because they can change shape. We can use them over and over, and they speed up the process. And they lower something called activation energy. Millions of reactions in a minute. They latch onto something. One thing, separate it, latch onto 2 things, 3 things, 6 things, put them together instantaneously. As fast as you can possibly imagine. And use them over and over again. They have a very, very long lifespan. So I will stop it here with enzymes and enzyme activities. There's a lot. And I'll have more, and I'll figure out a way to send you the other stuff that we might have missed. Let's hope it's actually recorded. It did. Oh, thank goodness for